Today I'm going to talk about, I would say the experiment we have done in the past several years related to, learn many different properties in solid-state quantum systems. And first off, I apologize if the talk had, less quantum but more materials. But you'll see the reason why, that's our focus. And we're going to focus on two general set of properties. One is electronic structure. The other is configurational properties. Okay. I'll say our exploration about machine learning, applying machine learning and AI for solid-state systems, really start from this topic, material genome initiative. So this was proposed by former President Obama in 2011. At the time, no AI, no machine learning for solid-state materials, right? The idea is that let's construct a database, a journal and public database to include all the available computational and experimental data for solid-state materials. So at the time, the first database was constructed by the Material Project located at Berkeley, and several other database was created later, but the journal size of the database is between 50,000 to 100,000. Okay, so that's essentially all the data we have. And the idea is that, okay, so once we have that, we can, take the structure from the database and generate some automatized workflow at the time. At the time, if you want to write a workflow, it takes actually several days to do this. But once you have that, you throw all the computational requests to, National Computational Facility, like at the time, Permuter and NERSC. And after you have all the high throughput computations, you generate some automatized, property analysis to analyze all the properties. And based on some criteria, you send the suggested materials list to your experimental friends. And if you're lucky enough, and for both of you, then you have functional material discovery, right? So I'll say that's the idea at the time. And I'll say many materials, functional material would discovered in this way, including material for catalysis, photocatalysis, and photovoltaic. But I would say at the time, around 2015 to 16, machine learning really entered this field. I would say initially, it's most related to organic material, but at the time, people start to use it for many inorganic materials. And the idea is that you grab some feature from the crystal structure database and use those features as input for machine learning. And you use the computed property as the target and use supervised learning to make predictions, which is much faster than first principle computations, right? And also you can design some recommenders and then use machine learning to suggest your experimental friend what the next experiment to do, right? Okay. And after several years of study of machine learning for solid, I would say my general picture is that the most essential thing for machine learning AI for solids is that you find this representation. This is a hidden representation in a multidimensional space, right? Whatever way you can find it, once you have it, you can generate a mapping between this multidimensional vector and the property you want to predict or study. And this property could be superconductivity or anything else. And if you take a look at the development of representation in the field for both molecules and solids, it goes from 2011 to 2017 or 18. And if you take a look at those representations, they have symmetry function, matrix, backup bounds, and or tensor representation, right? It becomes more and more complicated. But things stop around 2018. And the reason I think, we are very sure that is because of use of deep neural network, right? That becomes the mainstream. And one of the most important development is the graph neural network. And Boris has already given very nice introduction, so I can skip most of it. But I think I'd like to mention one important thing that for solid, when you build a graph, right, from crystal structure, you have to consider the periodic boundary condition, and also there's some special things related to the convolutional process. And the reason we really like this graph structure is that now you can represent everything by node and edge and interaction among them, right? And you can incorporate vector information for both nodes and edge. And this information can be elemental, spatial, or orbital based, right? So a lot of flexibility. And so if you take a look at the graph structure, right? So essentially you have node and edge. And the reason why it's powerful is that you can use this kind of, we call this message parsing scheme, to generate a message parsing message function and update the information in each node of the graph step by step, right? And then eventually use the readout function to read the information from those nodes in the graph and generate a graph pooling or node or edge pooling. Okay, so there are multiple ways to play with it. And I would say in the past several years, two very important developments. I think we have heard a lot of talk related to these two, right? One is the so-called attention, or a more complicated version, transformer, right? The other one is the equivariant neural network. The reason attention, I would say, based on my understanding, is powerful is that, previously, the information when you pass from one node to another node actually is just based on the edge, right? So this edge is kind of, I would say, fixed, and also you have to develop a cutoff radius to only include fixed number of neighboring nodes to make sure the convolution is efficient. But here, because you have this attention mechanism, now you can put weight in each node during the graph convolution process, and which actually makes this, I would say, much more flexible and powerful. And another development is equivariant neural network. And so in this case, yeah, I think Boris and Tess already gave a very nice introduction. So the most important thing for us is to convert everything in spherical harmonics. If you want to predict anything, beyond scalars, and then you use Clapeyron-Gordon coefficient to enable the graph convolution, right? But I would like to give several warnings if you use any of these two architectures based on our experience. First off is that the graph itself has permutation invariance. But because of that, when you do a graph pooling, actually there are only limited ways or choice, right? So you can do min, max, or sum pooling, but to keep this permutation invariance. But sometimes, only several nodes in the graph should be important at the end, right? You really want to get information from those nodes, right? And also, in graph convolution, there is a special problem which we call over-smoothing. That means that if you generate a very deep graph neural network with many convolution layers, the information at important node will be smeared out by this many times of convolution. So this issue has been recognized by the field. And if you use graph transformer to make scalar prediction, it's okay. But if you use it to make sequential prediction, many times, as Boris mentioned as well, actually, you can have this kind of stable, unstable prediction. You have a lot of oscillations in the sequential prediction. And also, sometimes graph transformer is less efficient than this kind of simple but fine-tuned graph neural network. Okay. And if you use equivariant neural network to predict anything beyond scalar, like a tensor and tensorial spectrum, you're going to see that the crystal symmetry constraint is not followed exactly. So you can train the model to follow roughly, but never exactly. Okay. So I think now we have some general introduction on why I entered this field and what kind of tool we are using. And now let's take a look at the whole landscape of computational physics or computational material science. And I'll say here I listed several different kind of atomistic systems and also different kind of methods, right? The reason solid state material is so complicated that beyond the crystalline system, you can generate a lot of different kind of much more complicated systems, like a dynamic system, right? And heterogeneous system, like a defect in solids, or heterojunctions, or this kind of similar structure. And also, you can generate alloys and disorder systems, right? And in those systems, you have so many configurations to consider, which makes the problem almost impossible for DFT to solve. And we start from density functional theory in many cases. And there are several, I would say, general research directions, right? So if you can use density functional theory to generate force and energy, right? And you can also generate the dynamic matrix and also derivatives related to force and energy. And from force and energy, you can generate interatomic potential, and then you can study dynamic systems. And from dynamic matrix, as Tess mentioned briefly yesterday, you can actually generate the phonon spectrum, get the phonon property. And from all the derivatives, you can put them in a density function perturbation theory, get the tensorial properties like elastic tensor, piezoelectric tensor, and so on. So that's one road. And you can also go to another road for different kind of properties, right? So you can predict the electronic structure of material from density function theory, and then you can use that to generate a linear tight binding Hamiltonian and use the electronic structure calculated by DFT to fit the Hamiltonian, right? And then you can compare that with model Hamiltonian and get topological properties. And also, I would say one important road is that from tight binding Hamiltonian, you can generate a response function, which I would say is pretty difficult to calculate if you go from this road, right? And this kind of tight binding Hamiltonian can be used for very large systems. They could be large scale or they could be heterogeneous. Okay. And the third road, in the field we have been developing is that, now you can go from a crystalline system, use DFT to calculate the energy. And because you have so many configurations, there's no way for you to consider all of them, right? So we can use I would say, more empirical method, cluster expansion, to read the finite number of energy from DFT and then calculate the configuration energy and generate input for molecular simulations, and then you can use that to study disordered systems, right? And I'll say so that is the full, I would say, learning pathways for solid-state quantum systems. And in the past years, the development of machine learning in this field essentially focus on two things. One is to accelerate density function theory calculation, right? Boris gave a very nice talk yesterday, and there have been industrial efforts from Google and Microsoft to generate deep learning density function to accelerate density function theory calculations. And the other road, I would say, is the road that bypass everything. So you really want to learn from crystal structure only as the input for your machine learning model. And then you want bypass density function theory and generate all the quantities I put the arrow here, right? So by doing this, you can greatly accelerate into the calculations and then enable the prediction of many complex properties of solids. Yeah, I think I can show you. I'm going to talk about several examples along this road. Okay. So today I'm going to talk about two application areas. So one is this in this electronic structure, and the other is this disorder system and configurational system. Okay. So one thing I really want to emphasize is the fact that we never have big data in our field of solid-state crystalline systems. So those are the rough estimation of all the available data in public material databases. And then the x-axis is the date complexity I defined, right? Those data could be scalar, volumetric data, matrix data, spectrum, tensorial spectrum, right? It becomes more and more complex. And then if you take a look at the number of data available, right, on the log scale, you see that we have a lot of structure, right? Recent work from Meta, they generate millions of structures. And for many of them, we have the formation energy. So it's on the level of 100,000. So if you have a machine learning model, if you learn crystal structure predict formation energy, it's easy, right? We have a lot of data. But now if you go to band gap, right, a very fundamental property of solids, the number now decreases to around 50,000, right? If you go to electron density on the same scale, and if you want to learn a tight binding Hamiltonian, right, the available tight binding Hamiltonian in the public database is on this order, around 1,000, 2,000. And density of state on the same level, but more complicated to predict, right? Band structure on the same level as band gap, I would say. We have around several 10,000 band structures available. And if you want to predict some more complicated things like a tensor, elastic, dielectric, piezoelectric tensor, the order of available data is around several thousand. And if you want to predict more complicated things, no data, right? So,
yeah, I just have a question. So here, when you're talking about computational data, you are mostly talking about DFT.
Yeah, DFT data created by.
We know DFT, at least in the naive way, is not accurate for some of these things. Like band gaps are
Yes. So, band gap underestimation by at least 50%. Yeah, right. Yeah, we know that.
So it may not be that great an idea to use those data, right? And in fact, the number of materials for which we know the band gap accurately from experiment is very small.
Yeah, exactly. It's on hundreds, right? On the order of hundreds. Yeah, that's the case. Yeah. So I think this question can be answered in two ways. First of all, even if you, so let's we really want high quality data, right? For instance, for band gap, we want the highest computational level, like a GW level or hybrid function level with adjusted mixing parameter. That's the best quality level you can have. But even if we only have, the data on the DFT level, like a traditional GGA or GGA plus U level, you can train the model, and the model can learn a lot of useful things. And if you have more higher levels of computational data, you can fine-tune the model. And the model already learned a lot of minimal things from the existing data. And you can fine-tune it with higher level data. And then the model will be able to predict the similar materials with higher level data. So that's one solution. And the other way is that I think the development of model and the acquire of high quality data, in many areas, they don't happen at the same time. Sometimes the model development is go beyond before the level of data. For instance, for image recognition, the image net appears much later than good convolutional neural network, right? Yeah. Okay. Okay, so the first question I would like to study is this electronic band structure problem. So the problem essentially is the energy of electronic state in the crystal momentum space, right? So if you go from the real space to reciprocal space and you study the electronic energy along those high symmetry lines, it can form a continuous line, and the eigenenergy of all the electronic state can be represented by those electronic bands, right? And the question is that whether you can use machine learning to make this kind of prediction. Okay, so in traditional way, we use density function theory. Boris has given a very nice introduction. So essentially, everything is represented by the electron density as a function of the density. And the density function, we have no unknown expression, and we have to have approximations. The lower level approximation, including LDA, GGA, and GGA plus U, as you heard that they all have inherent issues such as the self-interaction error, band gap problem, and so on. So you can use higher level theory, but they are more caustic. And also, if you take a look at this process, that you need an iterative process to find the ground state energy and also all the eigenstate, right? So this iterative process is slow. And another issue is the scaling of DFT. So the DFT scales with as order n cubed. N is the number of atoms. That means that if you want to study large-scale atomic state system, it's not accessible, right? Okay. So idea is that whether we can use machine learning to handle this kind of system, right? And so is a twisted bilayer 2D system and with a very small twist angle. And so there has been development using machine learning and deep neural network to predict a Hamiltonian matrix element based on the atomic orbital basis. But here, what we would like to study is that whether we can develop a very, very simple model with the least number of parameters and least number of nodes to enable this kind of prediction. Okay. Okay, so here we have to go back to think about the basis, right? So in crystal structure, we have the periodic boundary condition. So we have to follow the Bloch theorem, make sure that there's a phase factor for the wave function you used, right? But we can, based on this theorem, we can still construct a localized set, right? Atomic-like linear functions can be generated. So here, those are the generated linear function for the d orbital-like orbitals in MOS2. Okay, so now once you have the linear function, you can construct the linear function, linear Hamiltonian matrix, right? So now the matrix element just looks like that, right? So now you have multiple atoms, multiple orbitals, and the matrix element is determined by actually local atomic environment because you are using a linear function set that is very localized. So this essentially is a locality principle, and Javi discussed previously that because we have this nearsightedness of interactions, we can use such a tight binding Hamiltonian, and also it's helpful for us to develop a machine learning model for this. Okay. And here, because we recognize that it's very similar to atomic forces, so now our idea is that let's borrow the simplest, deep learning neural network for predicting forces. And this one, DeepMD is the first proposed, and I would say it's the simplest one, but very effective. The idea is that, in order for us to learn the local atomic environment, actually I just need 4 numbers. So if you have a central atom and a neighboring atom, you have this relative directional information, R, right? So now you just use these 4 numbers, 1 over R1, and the 3 component over R squared. Okay. So those 4 numbers give you a 4-dimensional vector. That tells you the interaction between these 2 atoms, this pair. So you can collect all the atomic pair information with a cutoff range, and then concatenate those 4-dimensional vectors to generate a longer dimensional vector, and put them into a neural network, and then generate the final input at the force, right, for this atom in this environment. Okay, so that's the idea. So now we want to borrow this idea and then use this to predict Wannier Hamiltonian element. The idea is that, okay, so now you can just use the block from DeepMD, right? So you learn essentially the same thing, but now you want to predict the on-site integral for the same, orbitals on the same atom. And then you can just read the same atomic environment information and generate the vector for DeepMD input. And then you don't want to stop here, right? You don't want to get the force only, but you want to start somewhere in the middle, get a effective lower dimensional representation for this local atomic environment. Okay, so let's say now you already have this. Another thing you have to vary is hopping between 2 orbitals on 2 different atoms, right? So here we found that if you only have the local atomic information for each atom, it's not enough. But you don't need to add many more. You just add a relative vector between these 2 atoms, 3-dimensional vector here, and concatenate these 2 local atomic environment vector. So now you can just use this vector to represent the hopping integral between orbitals on 2 atoms. Okay. So now we have on-site, we have the interlayer hopping, and now we can build the whole structure for simulating the electronic structure of twisted 2D system. There's one extra term, which is the interlayer hopping, right? Because we have bilayer system, the interlayer hopping is very weak. And we found that you can just use a 3-dimensional vector representing the relative direction between these 2 atoms in the 2 layers. That's more than enough. Okay. So now you see that it's a very, very efficient and very simple one based on, I would say, physics principle of understanding the interactions among these atoms, right? Okay. Okay. So now let me talk about the training side. So essentially, we are doing DFT calculations to get the atomic energies and also the atomic forces. And here we did around 10,000 bilayer MOS2, but in a much smaller supercell. And then we introduce random lateral or interlayer translation, very small ones. And also for around 3/3 of them, we perturb the crystal structure to represent all the possible local environment of atoms in twisted system. So now we use fast and Wannier entity to generate the Wannier function and the forces and energy. And the advantage of using Wannier function is that you see that per unit volume formula, so here we only need 17 orbitals for MOS2, right? Much smaller than the number you need if you use atomic orbital basis. Okay. And here we want to study this kind of twisted system with 2 different, rotation angles. Okay. Okay. So this is the result for the more relaxation of the bilayer twisted system, and those are the predicted forces. You see that the prediction actually is very, very accurate, right? It's on the level of million angstrom or per angstrom, right? And this is the relaxation created by DFT. And this is the relaxation created by machine learning predicted forces and using quasi-Newton method to relax the structure. Okay. If you compare them, they are very, very similar, right? Okay. And I would say most important thing for us, based on our initial motivation, is to get this, right? So we want to get the electronic band structure of those very large-scale atomic state systems. So this is the one for, around 9-degree twist angle. This one is for 3-degree twist angle. You see the comparison between DFT And machine learning result is actually, I would say, on the error level of milliards one, right? So very accurate. And the most important thing is this, right? So if you use DFT to do all the calculations, the computational time based on our estimation is on this line, on the log scale. But if you pre-train a model and use model to predict the twisted 2D band structure, this is the time you need for machine learning. So you see that there's at least 3 orders of magnitude difference in computational time for larger systems. Okay, I think that shows one way for us to machine learning electronic band structure, right? In a very simple way, but not universal. And we came back to the problem, and we actually, it's very interesting. It's ready to test comment yesterday. Can you just predict this electronic band structure with nothing? Just use a crystal structure, right? We thought about this problem, and the project started 4 years ago, actually. So we want to develop this end-to-end universal model to predict electronic band structure with nothing, just crystal structure. And here we have to make some compromise. So we have to use fixed number of bands close to Fermi level. So here we chose 6 to, because we only have A100 GPU, not B200, right? And we have fixed number of sample K points along the continuous high symmetry line. But I would say this model we developed is universal because we trained it on 28,000 electronic band structure available on the material project database for almost all the non-magnetic crystals. Okay, so now let's take a look at the architecture. Okay, so now you see that if you really don't want to incorporate physics, right, you want to start from scratch, end-to-end model, the model looks very complicated and ugly, right? Don't be scared about this. Let me give you some general, go through. So here, if you think about the representation of this problem, right? So you have a crystal structure. You need to generate some representation for the crystal structure, right? But think about this. Each electronic band is a sequence along K line, right? So now you have to represent K value in a high dimensional vector and concatenate these two to represent the system, right? So here we are using 2 things. One is this transformer-based graph encoder, which is here. It has multi-head attention and layer normalization and so on. And we did it twice, okay? And we are also using positional encoding for all the K points. So you want to actually increase the dimension of K point. So you cannot just use 3-dimensional to represent it because it's not enough to represent the variation in electronic bands, right? We have multiple band and a very strange variation. Okay. And here we are using a graph to sequence decoder to decode the information and generate the electronic structure.
So when you say position encoding of K points beyond just colonics in free space.
Yeah, sorry, I have a hidden slide, but I can show this. This is like the position encoded K point dimension vector usually. So this is the dimension we choose. Here, actually, we choose a pretty large dimension, 256. And each row here is a K point vector. The reason you have to do this is that 3-dimension is not enough because you want to predict this kind of variation in electronic band just based on K point. Actually. Yes, yeah, exactly. For the crystals with the same space group symmetry, we use a uniform set of K points. And here we are encoding the information in the K point, initial information. This will be updated, but Okay. And here I would say, even if you are using all of this, actually the prediction is going to be a disaster. And you're going to see that the prediction is going to highly oscillating, and also you're going to see a lot of kinks in the prediction. And here, the trick we are using here is the Fourier transformation. So we are trying to transform, we are going to transform the individual electronic bands into the frequency space. The reason we are doing this is that along this line, we have 128 points. But if you transform this into the Fourier space, right, frequency space, for each band, you just need to vary about those several numbers and those several numbers at different frequency, right? And also because electronic band is less highly oscillated, right? So here you're going to see that you only need to vary about the first several frequency numbers. And those essentially is a way for you to reduce the representation of the band and also make the prediction smooth. Okay. Yeah. So those are the prediction of the electronic band structure directly from the crystal structure. So I separate them into 4 quarters. And for the first quarter is the best one. You see that the black lines are the DFT result, and the colored ones are the prediction from our, we call this band former model. Okay. And you see that for some of the system, it's not good, right? But I would say it's also hard to tell why they're not good. I think that's kind of the common issue for machine learning, right? And yeah, the prediction accuracy for the band energies on average is around 0.3 electron volt. I would say that become usable, right? If you want to screen some material set, and you can use this machine learning model as the initial tool to screen them. And also, because we have the full band structure predicted, now we can predict derived quantities like the band center, band dispersion, and the band gap, right? The band gap prediction mean absolute error is around 0.2 electron volt. And for band center and band dispersion, it's on the same order. Okay, so sorry for running late. So now I want to come back to this general comment. So if you compare these 2 models, right, you see the pros and cons very clearly. So if you use Wonder, the first model, right, it's very accurate. And it's also, I would say, scalable, right? If you focus on the same material but larger scale, it's scalable, right? But it's not transferable. So if you want to work on another system, you have to retrain the model. And also, it's not universal, right? And the second model is universal, but I would say for some materials, it's not reliable. And you even don't know why only for those materials it's not reliable, right? I would say it's a dilemma for many machine learning models that are developing in the field for material science today. Okay. So sorry for running late. I'm going to talk about this part very briefly. Okay. So another question we have been very interested related to solid is the configurations. So for instance, in alloys, you can have multi-computational alloys, and the number of configurations is always huge, right? Really beyond the capability of DFT calculations. And here, if you think about the computation of this, binary compound, and in this very small cell, you already have 3 possible configurations. And if you create distortions or create vacancies, now you have many, many configurations to consider, right? And on each side, right, if you consider the elemental difference or you consider the spin difference, now you can have many different configurational disorder and to consider. If you have defects in the system, now you have structural disorder and vacancies and atomic distortions, right? So it becomes a very complicated problem, and the question is whether machine learning is helpful in this way. So very interesting, actually this problem has been studied in 1999 by actually expert in our field at Sanger. So the idea is that whether you can generate this as an inverse design problem, so to predict a very complicated alloy configuration with a given electronic structure, and in this case, is a band gap of the the alloy system. And at the time, Alex is using empirical model to predict the band gap and also the configurational energy. And here we want to see whether we can convert this to a machine learning problem. Okay, so if you take a look at the number of configurations and think about the properties, actually the configurational entropy is related to the density state, configurational density state of system. It means that you need to get the energy of all the configurations and calculate the configurational density state, which is this GE term. And from there, you're able to evaluate free energy, get the entropy, and from that, you can also get other order disorder related property like order disorder transitions and so on. Okay. But if you take a look at, we're using von Landau sampling here. And if you take a look at the number of configurations, right, it's on the log scale. And it tells you that you have to use some other method other than DFT to handle this, right? So in the traditional method, in the field of computer science, material science, they use cluster expansion. So here the idea is that you decompose the complex biological structure into those different clusters with different number of atoms, right? So now if you can evaluate the energy for each cluster and you just sum them up, you get the energy of the alloy system, right? But it's very effective in capturing these kind of short range orders, but it's not able to handle long range orders, distortions, or if you want to consider the properties other than energy of the alloy system, right? And the question is that whether we can kick out cluster expansion and put graph neural network here. Okay. And the answer should be yes. And Dr. Zheng Alfang in my group did this work. And the idea is that we just train the model with a given number of alloy supercells, right? So here we chose gold copper around less than 5,000. And those are the distribution based on the gold concentration, right? And we try to use graph neural network to predict the energy of the system. And you see that the error is around 2.6 millielectron per atom. So that actually is even better than the best cluster expansion model for this system. So it tells us it's usable, right? Okay. And now we can use the energy predicted by Qimin and use that as input for Monte Carlo. So now you do Monte Carlo and you switch the side, right? And you see that in order for us to get a very good converged configurational dense cell state, you need many, many steps for Monte Carlo, right? That means you need many, many configurational energies input, right? So here we found that at least you need around 4 times 10 to the 7th steps to get a converged configurational dense state, okay? So from that, you're able to get the entropy and the heat capacity of the system. We compare it with experiment, it's in the experimental range, okay? Okay, I think that's one step of success. And then we, a little bit ambitious, we thought, okay, so can we go one step further to incorporate the complex property of those alloys and evaluate this at different temperatures and compositions? But the problem is that if you want to, let's say you want to study optical conductivity, electrical conductivity, the computation itself is complicated and also it's sensitive to the K-point, the density of K-point mesh. And in principle, you have to evaluate that at each configuration, right? It becomes something very difficult to handle by any DFT code. And here our idea is that let's generate linear function in an automatic way and use that to compute many complex properties and train the machine learning model, enable the model to actually predict this kind of property for every configuration, and then combine them as an ensemble property. Okay. So that's our first step to generate the data. We essentially enable an automatic workflow to generate linear function for any solid state materials in the database. And I'm not going to go through the details, but from there, we generate some training data. And here, we want to use an equivariant neural network to check whether we can enable this kind of prediction of very complex properties. Right here, we chose, I would say, the most complicated properties, tensorial spectrum. So here we choose the permittivity tensor. So it's a tensor, right? And each tensor component is a spectrum as a function of photon permittivity. And you're using the equivariant neural network, and the most essential thing for us is to decompose this into you transform into the spherical harmonic basis. And also, we found that we need 2 channels, one L equals 0, and the other is L equals 2. Okay, so now essentially you can convert the spectrum in the tensor to different channels of the spherical harmonic in the spherical harmonic basis. Okay, so now because we are considering crystals, right? So we have crystal symmetry there. You can classify them into 5 different classes, right? And for different class, you see that this tensor representation for the permittivity tensor is very different, right? You have many non-zero terms for higher and higher symmetry crystal, right? You want the model to be able to learn this, then you can have some confidence with the model, okay? So here, this is a comparison between the target property computed by DFT and the prediction properties for all 5 different classes of crystals. So you see that, essentially it follows this trend, but again, you have to use a large number of data to train the model, and also you have to make sure the data covers all the 5 classes of crystals to give you this kind of property. And actually, we did this in this spherical tensor, I would say, basis, and we transfer it back. Okay. Okay, this is the general performance of our model. Also, here we, put them into 4 quarters, similar to the band structure prediction. And now we are using this. I'm going to skip this. Okay, to generate, I would say we call this a framework for modeling ensemble properties using machine learning. So the idea is that from machine learning, you get the ng of the configurations, and also you use the network we just developed to predict the spectrum or tensorial properties of the system. And now you just consider all the configurations during Monte Carlo simulations and calculate the ensemble, statistical ensemble of them, and use that as the ensemble property. Because of this, now you can evaluate the properties as a function of composition and also as a function of temperature. Okay. Okay, so here we are using these, I would say, effectively a two-dimensional alloy system. It's a MaxIn with different kind of surface termination with either oxygen or fluorine. But because of that, essentially on the surface, you have an alloy, right? Two-dimensional alloy. And we are using equivariant neural network with two different sets of input. One is we call it persistent homology feature to capture some defects on the surface. And the other one is the spherical harmonics, as the standard in equivariant neural network. Here we're predicting three things: optical conductivity, ng, and electrical conductivities, right? So now you can combine them to, so this is a prediction of ng compared with DFT. So again, very nice agreement. And now the capability of us is that now we can predict the optical conductivity as a function of the, the photon ng, and also the electrical conductivity as a function of temperature. And if you combine all of this, that's essentially what we can achieve. So now you can get the heat capacity information for different conditions at different temperature. And also we can get the information for electrical conductivity and optical conductivity also at different conditions and different temperatures based on the statistical ensemble. Okay. Okay, so I'm going to skip the explanation part for this. Sorry for running late. Okay, and go to the summary. Hopefully in this talk, I convinced you that the application of machine learning models, either simple or complicated model, in learning solid state quantum materials is feasible and it's doable, right? But it really depends on whether you can combine, put the physical informed information, physical principle, symmetry constraint in this framework, right? I talked about two different sort of applications: electronic structure and beyond, and also the configurational disorder and ensemble properties of alloys. Okay, and those are some publications related to these two set of works and the repository for machine learning models and also databases. Okay, yeah, I'd like to thank for my group members and the collaborators. Thank you so much.
Any questions for the speaker? Yes?
So, for instance, for electrical conductivity and so, do you compare to any experimental values, with this approach, or it's more of you just the stuff which comes out of DFT and quantity things, and compare it to those machine learning things?
What the second part of it?
So I guess
We compare with experiment, not a short answer.
Yeah.
But what the second part?
So I guess I wonder if you compare just to the DFT derived stuff, then it's surrogate ML model, or you also compare to any experiments.
Yeah. So actually, the motivation for us to study this figure actually is from Dr. Zhao Fang. So he was a student at UPenn, and we worked together with experimentalists to actually measure this figure, right? And as a function of the composition of oxygen on the surface, and also as a function of temperature. And they saw this kind of behavior, and it's pretty confusing to them at the time. And then we got the motivation to do this kind of thing. But I'm not showing the experimental data here, and we had consistent with some of them, not all of them, to be honest. But here, that's the motivation. And for the comparison, so here, essentially, we are comparing, when we train the model, right, we are comparing the prediction of optical conductivity and electrical conductivity with the calculated model by DFT, but not for these, so you can, so essentially, those you can compare with DFT, right? DFT calculates some, you compare with the DFT. But for the temperature dependence and the ensemble property, we only use machine learning. I think that's the motivation, right? You substitute the active file.
Quick question. I was looking at the result of the platform.
Uh-huh.
So, I think, did you see that each asymmetric points are protected by the symmetries? So those were learned by the...
So far it's not, to be honest. And 5 years ago, when I started this project, that's something I really want to incorporate, but I failed, to be honest. The initial idea for us is to use topological quantum chemistry to connect reciprocal space to real space and use a irreducible representation as a connection, right? So you have that, and then if you have that, degeneracy will be guaranteed, right? But we found that at the time, we don't have transformer, we don't have graph neural network. And we found that it's difficult to create one-to-one mapping between real space and reciprocal space. So it's difficult actually to build the convolutional layer when you connect real and reciprocal. But now I think it is something doable. And we have some ideas how to do so.
So I think it is crucial because you
Yes.
have to response.
Yes. So here, if you take a look at, the, that's not, let me find a good one. So here, right? So here there's a double degeneracy. But in the machine learning predictive one, there's a tiny gap. So it's not guaranteed. I think that's the point, right? If you don't include symmetry information in the model itself, it's not guaranteed, right? Even if you're using equivariant neural network, it's not.
Very nice talk. I just have a high-level question. So it seems like you start from the crystal structure, you are more biased toward short range or short length scale characteristic. But like for things like topology, it's more about long scale characteristics. So does that imply that it's not efficient to infer topology directly from the crystal structure?
It's a very interesting question. I don't have a direct answer to this. We have been thinking about incorporate symmetry information, the point group symmetry information in this, but it's just for the crystal unit cell, right? And that, in principle, can be incorporated. You just need to develop a different version of equivariant neural network. So these kind of things should be able to. But for long-range topology and symmetry, I think similar to what Tess mentioned yesterday, right? So if you go from unit cell to much bigger cell, whether you can tabulate all the available symmetry of topology is a big issue. If you can do that, you should be able to incorporate this in machine learning. And the first step for incorporating any symmetry here is to tabulate, for instance, the group table or Clebsch-Gordon coefficients, right? To tabulate things for the symmetry operation and convert that to something in the convolutional layer of the neural network. If you can do that, it's doable.
And then another side of that question is like, is it easier if you try to infer local property from the crystal structure? Like, if the two thing
Actually, I don't have slides. The reason we are incorporating this topological I'll say topological numbers, Betty numbers, right? You probably heard about this. This is used to identify the number of holes or number of connectivities in a network structure, right? The reason we are using this is to use it to capture local property. For instance, the formation of defect in a crystal structure. If you just blindly use a graph, the prediction accuracy is really, really bad. And Jay actually has a work on chemistry materials talking about this. But if you're interested, we can discuss offline.
Thank you.
A related question to the band former. So maybe also a simple one. You mentioned you use Fourier transform
Yeah.
to just keep some low frequency information, right?
Yes.
I was wondering whether you're taking a one-dimensional Fourier transform or if it's folded.
Yes. So right. So
Hints, right? I symmetry point that includes some high frequency.
yes, exactly. So if you actually we did this along this continuous K line, we have to, right? Because if you do it in the uniform K space, it's not doable for us. We don't have data. If you do it instead, that's true that you have some kinks when you go from one branch of band to another branch at a given high symmetry point. It's going to generate some artificial high frequency component.
Like
we thought about it. It's just expensive. You can do this. It just become very expensive. Yeah.
Other questions? Let's thank Qimin again.
Thank you so much.